So since these changes in the geostrophic wind with respect to height are related to thickness, it seems like we should be able to learn about it by looking at maps of thickness. So let's do that. Here is an old school map. Difax map, happens to be January 2004, but they still make these things. The solid contours on here are pressure at the surface, so we're looking at the patterns of like cyclones and anticyclones. And the dashed contours on here are contours of thickness. And let's just zoom in on North America here. And I'm looking at this pattern right here, and boy, there's a lot going on. These are a little hard to read, but we'll work our way through it. And I'm going to superimpose on here the equation that we're going to be using for the thermal wind, UT and VT. And I'm going to pick a point. I've got a point there in Alabama that has that little yellow circle on there. And I'm going to use this map of the pressure at the surface and the 1,000 to 500 millibar thickness to tell me something about what's going on with the thermal wind. So let's actually take that point and make kind of a little big plus sign here. We're going to talk about the point to the north, the point to the south, the point to the east, and the point to the west as our way of approximating these, making a finite difference approximation to these partial y and partial x terms. And if I think about the UT equation, okay, UT, thickness is decreasing to the north. If you look at these contours as we go from the south side to the north side of the box, south side to the north side of the plus sign or whatever, you can see that we are decreasing as we go to the north. So that partial thickness, partial y term is going to be negative. But there's a negative sign in front of the whole thing. So your result is that UT, the thermal wind's zonal component, is going to be positive. It's going to be from the west. On the other hand, at that particular location, let's look through VT. VT is, we're going to be looking at the changes in thickness in the x direction. And if you take a look, it's basically constant at that location in the x direction. We're at basically the same contour on the east side and the west side of that plus symbol there. So in this case, VT at that location is 0. So, okay, if I wanted to actually draw what my thermal wind vector is going to look like at that location, it looks like something like this. Here's big VT, the vector. All right, it's that orange vector that's on there. In fact, we could have done this at lots of locations on this map, and what we would have found is that our thermal wind vectors are parallel to contours of thickness. They have low thickness to their left and high thickness to their right, and they get longer and stronger the closer together the thickness contours get, the stronger the gradient gets. It works very much the same way like geostrophic wind works, except geostrophic wind uses height contours. Now we're using thickness, and this is the thermal wind that we're looking at right there. Now, let's think about what that actually means for our location there in northern Alabama. That location is on the east side of an anticyclone in this case, and I've just sort of drew a blue arrow there helping you realize which way the winds are rotating around there. Now, the winds are not geostrophic, nor are they, for that matter, in gradient balance, because that is actually surface pressure that's on there, but we can certainly compute a geostrophic. There's nothing that stops us from being able to compute a geostrophic wind at that location. It may not be what the real wind is doing, but it's always going to be an approximation to what the real wind is doing. And at that location there, if I wanted to make a geostrophic wind that is parallel to the isobars at the surface and so on, it probably would look something like that at that blue dot there. It would be parallel to the isobars at its location. All right, great. It's probably not a terrible approximation to what the real winds are doing, actually. Now, if I superimposed on that what the thermal wind vector looks like, and think about this as being, oh yeah, we have this way of thinking about it as a vector addition, where we take the geostrophic wind at the lower part of the level and add the thermal wind, we should get the geostrophic wind at the upper part of the level. So if blue is the geostrophic wind at near the surface, or 1,000 millibars or something like that, then add our thermal wind to that, our resulting vector is that green vector. That should be the geostrophic wind at the top of the layer, namely 500 millibars in this case. So that would be approximately what our geostrophic wind at 500 millibars would be doing. Maybe it's part of a ridge or something like that. Now, that is then what's being created by the temperature. That is a change in the geostrophic wind at different heights being caused by that temperature gradient here. And notice how the wind changed with respect to height. In this case, the wind was changing counterclockwise with respect to height. The winds down there near the surface that were in that blue are then, as we go up with respect to height, the winds are rotating counterclockwise. There's a vocabulary word here, backing. Backing is when winds change counterclockwise with respect to height. And counterclockwise rotation with respect to height and backing is associated with cold air advection. Let's talk a little bit about cold air advection just for a second here. See how the wind at this location at the surface is blowing parallel to height contours, or pressure contours in this case, and it is blowing across contours of thickness from cold towards warm air. Well, anytime you have a wind blowing across contours like that, you're going to be making these little boxes, these little diamonds on here that are called solenoids. See how there's all these little diamonds on here? These little diamonds are called solenoids. Anytime you have a whole bunch of those little diamonds out there, you should be thinking about advection. Now, you're going to be watching a second whole video that's about finding advection on a weather map. If you aren't familiar with this technique, you will be figuring out how to find advection on a map like this. But smaller little solenoids, those little diamonds, the smaller and smaller they get, the stronger and stronger the advection is getting. So this area that I have circled in blue, where we see the two sets of contours crossing and making those little diamonds, is an area of cold air advection. And throughout that area of cold air advection, the winds are backing. We could do a similar analysis for the wind, the thermal wind at that location up there in Kansas, right? Well, if we did it, we'd already find out, though, because we don't need to work through all the signs and everything. We know that the thermal wind will be parallel to the contours of thickness. And we know that the wind at the surface is basically parallel to those isobars, if we're assuming that's the geostrophic wind anyway. Again, it's probably not, but it's probably not a terrible approximation to it. Well, once again, if we do our little vector addition trick where we're adding the thermal wind to the wind at the low level, the result will be our wind at the top of the layer, which in this case is 500 millibars. So our green vector there is the wind at the top, the geostrophic wind anyway, at the top of the layer. That's the 500 millibar geostrophic wind. Notice how the winds are changing with respect to height. This time, as we went from the low-level wind, which is blue, to the upper-level wind, which is green, the winds are turning clockwise with respect to height, and that's called veering. Veering is always associated with warm air advection. So here's an area of warm air advection. Again, see how the two sets of contours are crossing each other and making little diamonds called solenoids? This is an area that we could identify as having warm air advection. And throughout that region, the winds are going to be veering. They're going to be turning clockwise with respect to height. How do you keep it straight? How do you remember which one is veering and which one is backing? Well, the names are kind of easy to keep straight. Backing is cold air advection and veering is warm air advection. Notice how B is right next to C in the alphabet, so backing, cold air advection. V and W are near each other in the alphabet, so veering, warm air advection. So that part is kind of easy to keep track of. It's keeping track of which one is clockwise and which one is counterclockwise that I have trouble with. Here's how I remember it. Let's go back to a diagram like this of a cyclone here, where we've got winds rotating around it, and on the east side of it, the winds are out of the south, and there's warm air advection happening, and on the west side of it, there is winds are out of the north, and there's going to be cold air advection happening. So you can see I've got these kind of surface winds drawn in here as a blue arrow and a red arrow. Well, aloft, above this whole system, the winds are going to be more or less westerly. Okay, I mean, whether we're in a trough or a ridge, whatever's going on, I mean, we're presumably in a trough, but whatever, the winds are going to be more westerly aloft. How do we get there? How do we get from at the surface having winds out of the south or out of the north to having winds aloft that are out of the west? Well, in the area of cold air advection, the winds are going to be turning counterclockwise with respect to height. See how the winds are like out of the north at the surface, and then they become more out of the northwest, and then out of the west-northwest, and then eventually out of the west-northwest, and then by the time we get to the top, they're out of the west. The winds are turning counterclockwise with respect to height. On the other hand, in the area of warm air advection, the winds are out of the south, maybe they're out of the southeast even, and then south-southwest, and then maybe southwest, and then maybe at another height, west-southwest, and by the time we get to a higher height, the winds are basically out of the west. The winds are turning clockwise with respect to height. Okay, now that you've watched this, I want you to go and watch the video that's about how to find advection on a weather map, because I know that sometimes that's something students aren't familiar with already. And the link to do that is in blue line. All right, please let me know if you have any questions. This has been Dr. John Schrage.